Hello everyone, my name is Dylan, and today we're going to go over problem 3.17. This asks us to derive P3 of x from the Rodriguez formula and check that P3 cosine theta satisfies the angular equation 3.62 for L equals 3. Additionally, we need to check that P3 and P1 are orthogonal by explicit integration. Let's start off by writing the Rodriguez formula for Legendre polynomials. This can be written as P sub n of x is equal to 1 over 2 to the power of n factorial multiplied by the derivative with respect to x n times, and then x squared minus 1 to the power of n. Since we're finding P sub 3 of x, n is going to equal 3. So if we just plug that in, what we'll get is that P3 sub of x is going to be 1 over 48 times the derivative with respect to x, and we're doing that derivative 3 times of x squared minus 1 cubed. And the reason we get 1 over 48 comes from the fact that 2 to the third power is 8 multiplied by 3 factorial, which is 6. So you get 1 over 8 times 6, which is 1 over 48. And then our next step is to start taking their derivative. So if we take the derivative of this, we get 1 over 48 with the derivative with respect to x multiplied by 3 x squared minus 1 multiplied by 2x. And this can be simplified further. 3 times 2 is equal to 6, so 6 over 48 becomes 1 over 8 multiplied by the derivative with respect to x of x times x squared minus 1 squared. And then what we're going to do is that we're going to take the derivative of this. So we get 1 over 8 with the derivative with respect of x, and then we're going to have x squared minus 1 squared plus 2x x squared minus 1 multiplied by 2x. What we can do here is factor out an x squared minus 1, as there's a common term. And then, so that way we'll get 1 over 8 multiplied by the derivative with respect to x of x squared minus 1 of x squared minus 1 plus 4x squared. If we simplify this, we get 1 over 8 multiplied by the derivative with respect to x of x squared minus 1 multiplied by 5x squared minus 1. Now we take the derivative one more time, and we get 1 over 8 2x 5x squared minus 1 plus 10x x squared minus 1. We can factor out 2, so that way we get 1 over 4 5x cubed minus x plus 5x cubed minus 5x. this becomes 1 over 4 10x cubed minus 6x, which becomes, and I'm going to keep the 1/2 outside, 1/2 multiplied by 5x cubed minus 3x is equal to p sub 3 of x. This is our answer for part 1 of the problem. The next part of the problem asks for us to check that P3 cosine theta satisfies the angular equation 3.60 for L equals 3. Now the angular equation, and I'm going to substitute some terms here from the book, is that we have d theta multiplied by sine theta dp d theta is equal to negative L multiplied by L plus 1 sine theta p. Now in the book, what you would usually see is that instead of the term p, you would see a capital theta. However, because we're just going to be solving in terms or checking for that P3 cosine theta satisfies the angular equation, this is essentially going to be replaced anyway. And then what I'm also going to do before we move on to actually solving this is that we're going to find, I'm going to put I'm going to put the sine theta on this side, so that way we have like terms. And so we'll have 1 over sine theta multiplied by the derivative with respect to theta of sine theta of the derivative of P3 with respect to theta. And then that's going to equal the negative L multiplied by L plus 1 times P. And so what we're going to do from here is we're going to basically do each derivative on its own and then combine it all together. So let's start off with just this term right here, the dp3 of d theta. So the derivative of p3 with respect to theta is going to look like 1/2 multiplied by negative sine theta multiplied by 5 cosine squared theta minus 3 plus cosine theta multiplied by 10 cosine theta multiplied by negative sine theta. And the way we get this is that for up here, instead of 3p of x, we just plug in cosine theta. So this is going to become 5 cosine theta cubed minus 3 cosine theta. And this is our derivative here. And then what we can do is we can simplify terms. So that way we get negative 1 over 2 sine theta. We're going to factor out this sine theta here. We get 5 cosine squared theta minus 3 plus 10 cosine squared theta. If we combine the cosine squared theta terms, that becomes 15 cosine squared theta, and then we can actually factor out 3. So what we get is negative 3 over 2 sine theta multiplied by 5 cosine squared theta minus 1. And that is the derivative of P3 with respect to theta. However, that's only the first part. What we now need to do is take the derivative with respect to theta of sine theta of the derivative we just found. So if we do that, what we're going to have is the derivative d theta sine theta dp3 d theta is going to equal negative 3 sine theta cosine theta multiplied by 5 cosine squared theta minus 1 minus 5 sine squared theta. And then from here, we can divide this by 1 over sine theta, because again, we have this term out here that we still haven't multiplied by what we have here. And so what we're gonna get is actually negative 3 cosine theta multiplied by 5 cosine squared theta minus 1 minus 5, and then in parentheses 1 minus cosine squared theta, and we get this 1 minus cosine squared theta using trig identities, because this is sine squared theta, and we're just simply rewriting it. So that way it can be simplified later, and we get negative 3 cosine theta multiplied by 10 cosine squared theta minus 6. You can factor out a 2 here, but instead what we're going to do is factor out 4. That is because we get negative 3 multiplied by 4 multiplied by 1/2, which is multiplied by 5 cosine squared theta minus 3. And what you'll notice is that, oh, sorry, wait. I also forgot the cosine theta outside here. There we go. And what you'll notice is that this right here is actually just our P3 of cosine theta term, which is what we started off with. And so negative 3 times 4 times 1/2 cosine theta multiplied by 5 cosine squared theta minus 3 is equal to negative L multiplied by L plus 1 multiplied by P3 cosine theta, where L equals 3. And what would happen is that basically both sides of these equations are equal to each other, which is what we want. If we plug in the 3 for the L, we get negative 3 multiplied by 4 multiplied by our P3 cosine term, which is what we have up here, and it's also the same thing as this term on this side. This shows that they're equal to each other from the angular equation. So, with that in mind, that only leaves us with one part left, and that's to check that P3 and P1 are orthogonal by explicit integration. We'll know that they're orthogonal by integration if our end integration is equal to 0. But before we can do that, we need to know that P1 of x is equal to x. And that we already know our P3 term. It's 1/2 multiplied by 5x cubed minus 3x. But we need this for the integration. And that is because we're integrating from -1 to 1 of P1 of x multiplied by P3 of x dx. So when we plug this in, the integral from -1 to 1 is x multiplied by 1/2 5x cubed minus 3x dx. We're going to bring out the 1/2 out front. We're going to multiply this x into the parentheses here. So our integral is actually going to be 5x to the fourth power minus 3x squared dx. And when we actually integrate this, what we're going to get is that 1/2 5x to the 5th power over 5 minus 3x cubed over 3 from -1 to 1. The 5s are going to cancel out, so are the 3s, and now we just plug in our 1 and -1. So what we'll get is 1/2 of 1 to the 5th power minus 1 to the 3rd power minus, I'm going to put parentheses here, -1 to the 5th power minus -1 to the 3rd power. And what you'll realize is that this goes to 0 and this also goes to 0. So we just have 1/2 multiplied by 0, which is equal to 0, which proves that this is orthogonal. And with that, we have solved every step of the problem. We have derived P3 of x, which we have stated as up here is 1/2 5x cubed minus 3x. And then on top of that, we check to see if the P3 cosine theta satisfies the angular equation. And we found that it does, as both sides are equal to each other. And we have proved that it's orthogonal. Thank you.